Here's our equilateral triangle again. We put an XY coordinate system here with the origin in the center of the triangle, and then labeled the corners x1, x2, x3. And we discussed the symmetry group of this equilateral triangle before. So there is, of course, the identity, and then we have rotations at 120 degrees, clockwise or anti-clockwise. One is the inverse of the other. And then 3 reflections, which we call sigma 1 to sigma 3 now, across these axes here. So reflection across this axis here would be sigma 3, and so on. And here we also indicated what these correspond to when we identify D3, the symmetry group of the triangle, with S3, the permutation group. Next, we introduce some functions here, these phi j's, which are Gaussians centered at the corners of the triangle. So let's say it could look like this. If you put one here in the x2 corner, and maybe this is what it looks like. And now let's see what happens when we apply our OA operators. So the A's are now just these group elements here. We apply these OA operators to the phi j's evaluated at x. That is, by definition, phi j evaluated at A inverse x. And now let's substitute phi j here, so it's e to the minus. And now we have A inverse x minus xj mod squared. Pull out an A inverse here, so A inverse x minus, and then we need an A xj here, squared. And now, since all these operations are orthogonal, just rotations and reflections, the A inverse here wouldn't change the length of this vector, so we can just omit it and get e to the minus x minus A xj mod squared. So what we do is, when we reflect, say, across this axis here, then we move the Gaussian up here. Or if we rotate clockwise, let's say 120 degrees, then we move this Gaussian here. And you see, wherever we start, by applying the group elements of our symmetry group of the triangle, we always end up in one of the corners again. So the span of the functions phi 1, phi 2, phi 3 is an invariant subspace of some function space where these phi's live in. Don't care about which space we put them in now. Now you can do this. Pick one or two of the group elements and work out what the representation look like. There are 3 by 3 matrices which would map a vector, a linear combination of phi 1, phi 2, phi 3 to some new linear combination of phi 1, phi 2, phi 3. So stop the video here for a moment, work out such matrices. And now that you've done this, you can compare to the results which I've written down here for you. And of course, we've seen these before, since this representation just permutes the phi's. This is just the representation which we had before when we drew the bird tracks next to a 3-component vector and just permuted the components of the vector.